Place 2 glasses beneath the same light source. Both glow with a warm amber hue, a color that makes our brains think of honey, aged wood, and time itself. Yet interestingly, that color reveals nothing about the original energy sources that created them. One begins with the rigid starch of barley glucose molecules locked tightly within the polymer networks of amylose and amylopectin. The other emerges from simple sugars already prepared for fermentation inside ripe grapes. One is a system that must be unlocked by enzymes, the other has been pre-processed by sunlight long before it reaches the distillery. So why? After years in wooden barrels, do they look so similar? To answer that question, we must look at chemical structures. The thermal decomposition of oak. The history of early 18th century copper stills. And the moment humans learned to control a process that was once chaotic by nature. Because amber color is not a coincidence. It is the result of a chain of reactions, sometimes deliberately engineered. Sometimes discovered by accident across centuries. Starch and sugar are both carbohydrates. Yet structurally, they are fundamentally different. Starch in grains is a long polymer of glucose. It exists to store energy for seeds, not to feed microorganisms. Glycosidic bonds alpha 1 and alpha negative 6 form a network that resists easy breakdown. To transform it into ethanol, humans must activate amylase enzymes through germination, a technique already practiced by Mesopotamian communities more than 5,000 years ago. By the 16th century in Scotland and Ireland, controlling the malting process had become a crucial skill. Producers did more than dry barley. They burned peat, releasing smoke rich in phenols, aromatic ring compounds capable of bonding with proteins and creating the signature smoky aroma. Here, flavor begins with the chemistry of the land itself. Grapes, by contrast, contain glucose and fructose monosaccharides that ferment easily. Saccharomyces cerevisiae converts them into ethanol and CO2 through glycolysis and alcoholic fermentation. No polymer needs to be unlocked. No additional enzyme activation is required. This difference shapes the entire flavor architecture that follows. Whiskey carries the memory of starch breakdown and sometimes traces of phenolic smoke. Brandy preserves fruity esters, volatile molecules such as ethyl acetate or isoamyl acetate, responsible for floral and ripe fruit notes. Two liquids. Two entirely different biological systems. Distillation is not the separation of a spirit. It is an application of boiling point differences. Ethanol boils at 78 bayak, lower than water. When heated, ethanol-rich vapor rises first. As early as the 8th century, Arab alchemists developed copper alembic stills. Copper does more than conduct heat efficiently. It reacts with sulfur compounds, removing unpleasant odors during distillation. By the 18th century, copper pot stills in Scotland became the standard, producing spirits with heavier compounds that preserved a robust body. Brandy, particularly in the Cognac region, relies on double distillation in Charentai's copper stills. This method is more refined, retaining aromatic esters while eliminating heavier impurities. Here, physics shapes personality. Whiskey often allows higher levels of congeners, secondary compounds such as fusel alcohols or aldehydes, creating a bold, sharp texture. Brandy leans toward controlled purification, protecting delicate fruit aromas. Distillation, therefore, is not merely a technique. It is a philosophy about what to keep within the chaotic mixture created by fermentation. If distillation is refinement, barrel aging is long-term transformation. Oak contains lignin, hemicellulose, and tannins. When the inner surface of a barrel is charred, a practice common in 19th century America, lignin thermally breaks down into vanillin and seringaldehyde, producing notes of vanilla and spice. Hemicellulose caramelizes, generating compounds that contribute golden brown color. More importantly, wooden barrels are not completely airtight. Oxygen slowly diffuses through microscopic pores, driving gradual oxidation. Ethanol reacts with organic acids to form new esters molecules that deepen aromatic complexity. Seasonal expansion and contraction push the liquid into the wood fibers and draw it back out again. This repeated diffusion and extraction acts like a slow circulatory system. Both whiskey and brandy undergo this same mechanism. That is why both develop their amber tone, a result of phenolic compounds and caramelized sugars extracted from oak. The colors match, but the underlying molecular compositions remain distinct. Amber does not originate from grain or grape. It comes from the reaction between a clear liquid and oak wood. When lignin undergoes thermal breakdown, it releases aromatic aldehydes. Exposure to oxygen triggers further reactions, forming more complex and stable structures that anchor the color. It is a kind of organic rust, slow oxidation, producing shades of golden brown. Interestingly, the human brain associates this color with age and value. In color psychology, golden brown tones evoke warmth and permanence. Producers understand this. In fact, during the 19th century, as industrial demand grew, some makers added caramel coloring to standardize appearance proof that vision can be guided as much as chemistry. So two glasses may look alike not because they are the same, but because they have passed through similar chemical environments: oak, oxygen, and time. Whiskey and brandy may share an amber glow, yet their biological energy sources, molecular structures, and technical histories differ profoundly. One begins with starch polymers that must be decoded. The other starts with simple sugars ready for transformation. One carries traces of peat soil and cold climates. The other carries sunlight and vineyard ecosystems. This reminds us that in engineering and in life, surfaces rarely reveal structure. Two creations can appear identical because they traveled through the same environment of transformation, yet their essence is determined by their original source of energy. And perhaps that is what has truly been distilled over 5 centuries of history, not merely alcohol, but humanity's growing ability to understand and control nature's chemical reactions, crafting architectures of flavor that seem simple at first glance, yet are in reality a symphony of physics, biology, and time.